What I'd like to talk about is I'd like to give an exposition of primarily Witt vectors, and this will be from a point of view which is different from what most people are familiar with. So I guess what I wanted to say, I think it's better for kind of on a purely expository basis to think about to kind of introduce them in this way. And I also think that even if you're an expert or you know something about Witt vectors, you'll kind of get something new if you out of this if you haven't seen this approach. So the goal then is basically the advantage is it gives a formula-free approach to the Witt vectors. If you've ever seen any expositions of any introductions to Witt vectors before, they're completely written with formulas, and which means to prove anything about them, you always have to go back to the formulas. I'd like to. So what I'm proposing, which is, I mean, this is not new to me. Basically, André Joyal is the one who first, I think, who maybe gets the most credit for coming up with this point of view. This will be a formula-free approach to the Witt vectors. However, the point of view I'm going to take is actually using formulas. So it's a kind of a, well, you'll see. The formulas from this approach could be easily eliminated, but I think it'll be a little clearer to actually write down some formulas. But then you'll see that they're actually not essential. Whereas in the more traditional approaches, the formulas really are essential. Okay, let me begin. The first section is on p-derivations and delta rings. Okay, so we'll fix a prime p. This will be fixed through this entire series of lectures. And R will be a ring, commutative, as always in this series of lectures. A ring endomorphism, so phi from R to R, a ring endomorphism, is said to be a Frobenius lift I'm defining the term Frobenius lift here. Well, if it lifts the Frobenius map. So if, now let me write down a formula, for all x in R, phi of x is congruent to x to the p mod PR. So modulo p, this map reduces to the usual pth power Frobenius map on R modulo p. So just a few examples to get things straight. So R could be, for instance, polynomial ring in one variable, and phi could be the map, which on the generator here, x sends x to the p plus p times anything. So there are many rings with Frobenius lifts. Also in global class field theory, the ring of integers of a number field has Frobenius lifts at all the unramified primes, say an abelian. I guess you probably don't need abelian. Also in crystalline cohomology, these things come up. And finally, in algebraic K theory, they come up as Adams operations. Psi p. Okay, so they're important things. So the goal of this series of lectures is to show that the concept of Frobenius lift leads inevitably to the concept of Witt vectors. Somehow you can't really avoid it. It's not even that to explain how you could have thought of Witt vectors yourself, but how you must have thought of them yourself if you had thought about this. So, okay, so that's our goal. So, however, the concept of Frobenius lift has a problem, which is this. you can look at the category of rings with Frobenius lift. This naturally forms a category. So by that I mean the morphisms are just ring homomorphisms which are compatible with the given Frobenius lifts. But it's not a good category. So let me say ... but not a good one. So it fails to have some properties that you might want in a category. And the problem, maybe should I, let me give you a little exercise, exercise 1. It does not have so-called equalizers and morphisms. Meaning, so I guess I won't assume in this series that you know too much about category theory, but I'll assume you know a little bit. So if you have two rings with Frobenius lift and two homomorphisms in the same direction between them, you can look at the subring of A on which the two agree. And A will have an endomorphism, the phi here and the phi here, they're compatible, so they'll restrict to a phi here, but it won't necessarily be a Frobenius lift. And the problem, the reason why that happens, is that the word lift has a hidden existential quantifier. Has an existential quantifier hidden in it. What do I mean? I mean, let me just write out this in kind of more detail. It means for all x, there exists an x prime such that phi of x is equal to x to the p plus px prime. That's just what the lift condition means. But this x prime, but x prime is unique only up to p torsion. Right? Obviously, if you add a p torsion element to x prime, this equation will still hold. So in the presence of p torsion, you have no control over what this x prime is, which is bad. It kind of prevents you from doing things. In the p torsion free setting, then x prime, if it exists, is unique. So then you do have complete control over everything. And then the concept of a Frobenius lift is exactly the right thing. But in the presence of p torsion, it's not. It's sort of only an approximation to the right concept. Okay, so our solution to this is what is kind of a standard thing, which is to make the data of x prime part of the structure. So how did I want to, maybe I'll say this. Provide x prime as part of the structure on the objects and the categories, the category we want to define, rather than the property of its mere existence. That's how I wanted to say it. Of course, this is a common thing in mathematics and higher category theory. If something exists but is not unique, you really want to give that object as part of the structure rather than just require that some such object exists. Okay, and this will solve all our problems. So, i.e., we want an operator, which I'll call delta, which goes from R to R, modeled on delta of x is 5x minus x to the p divided by p. So that, right? So this, where did I write it? I have an x prime somewhere. Here. So this x prime is meant to be our delta of x, kind of using both notations to make you think of a derivative. We'll get to that in a little bit. So we want to have an actual operator. So there's a particular, so this is our x prime. So there's a particular x prime. Okay. So what then are the axioms? Well, what you do is you just, so giving yourself such an operator, using it, you can define a phi from delta. So maybe I should write that down. You can define phi of x. If you're given just a random set map, but we're thinking about it this way, you can define phi of x by this. This obviously reduces to the Frobenius map modulo p, but it might not be a ring homomorphism. So to make this a ring homomorphism, we just write out the axioms for phi to be a ring homomorphism, but then solve for delta. So let me do that for you. And this is really the key point coming up. So first we'll do additivity. So you have an axiom which says this. And now we want to express everything in terms of delta. So we just write that in terms of delta. So this is x plus y to the p plus p delta of x plus y. This should equal x to the p plus p delta of x, and then y to the p plus p delta of y. And now we want to solve for delta of x plus y, so we can just rewrite this. So this condition here is equivalent to the additivity of phi, but you'll notice that that everything in here is divisible by p. So if you expand this out using the binomial theorem, all the intermediate coefficients are divisible by p. So in fact, this axiom is completely equivalent to this axiom. But there's an axiom which is equivalent to this only in the case where you have no p torsion, when you can divide by p, and that's this one. So I'll write a squiggly arrow. And then what is this? This is minus the sum of 1 on p choose I, x to the I, y to the p minus I goes from 1 to p minus 1. So this axiom here, if we interpret it as being true only modulo p torsion, then it's equivalent to the previous one and hence equivalent to this. But we want to interpret it, we want to take it as being exact on the nose, in which case it's a stronger, it implies this axiom here, and hence the additivity of phi. It is equivalent to it in the case if the ring is p torsion free, but in general, it's a stronger axiom. So I'll call this axiom 1. And then we do the same thing for the other ring homomorphism axioms. So yeah, for multiplicativity, we have this, which then gives us this, which if you expand out, you'll see the x to the p, y to the p will cancel the x to the p, y to the p there. Then all the other factors will have multiples of p, which you can divide by. We'll play the same game, but I'll do it a little quicker here. And we get delta of xy is x to the p delta of y plus delta of x, y to the p plus p delta of x delta of y. And this is axiom 2. And finally, a ring homomorphism has to preserve 1 and 0. I guess 0 is kind of follows automatically, but let me write it down anyway. It's a redundant axiom. It's just that if you substitute in 0 here, you get 0 equals p times delta of 0. Again, you divide by p, and you get delta of 0 is 0. As I said, that's a redundant axiom. But one which is not redundant, if you substitute in 1, you get 1 equals 1 plus p times delta of 1. And again, you play the same game, and you get this. So these are our 4 axioms. Okay, okay, so let me just say this quickly. A p-derivation is a function, a set map, delta from R to R, satisfying axioms 1 through 4. And a delta ring is a ring R equipped with a p-derivation. You might be wondering why this is called a p-derivation. What does it have to do with differentiation? And I mean, first of all, it's just a name. It shouldn't be taken too seriously, but I think it's a good metaphor. If you look at this, if you take this equation and reduce it modulo p, this term disappears, and then you get exactly the usual Leibniz rule from differential calculus, but twisted by Frobenius. So for that reason, you might think of delta as some kind of arithmetic version of a derivation. And in fact, Bouillon has written many, many papers where he kind of really taking the analogy, delta is the derivative with respect to the prime number p, seriously. Okay, one more comment. You might also, it's really more a matter of language. What I'd like to do is think of these 4 axioms as Leibniz rules for the operator delta with respect to addition, multiplication, additive identity, and multiplicative identity. So unlike, here's the Leibniz rule for delta with respect to multiplication. It's very similar to the usual Leibniz rule. But delta is not additive in general. So there's a similar Leibniz rule. Similarly, there's a different Leibniz rule for delta with respect to addition. And the presence of this kind of makes, this is the only way in which Witt vectors are more complicated than something you're really very familiar with already. Okay. So before I say that, if you have a p-derivation on R, then what you can do is you can make this Frobenius map, where 5x is defined, it's the same formula I've written many times. You define 5x that way, and that will be a Frobenius lift. So we have a function from p-derivations on R to Frobenius lifts on R. This is a bijection if R is p-torsion free. But is not a bijection in general. That's kind of the whole point. But if your ring R is p-torsion free, then giving a Frobenius lift is equivalent to giving a p-derivation on R. So you know many examples of delta rings already. So examples of delta rings: one, any p-torsion free ring with Frobenius lift. So for instance, we could do the ring Z bracket X, which I had written right here. And then you'll remember phi of X sent X to the P plus P times anything. That P times anything, that anything was exactly the delta. So in fact, delta of X can be anything. Where now X, here X is not a variable, it's that specific generator. Should I don't know. I'll leave it. So also algebraic K-theory, if you take K0 of a sufficiently nice category, let me not try to be precise about that, say vector bundles on a manifold or locally free sheaves of finite rank on a scheme, coherent sheaves of finite rank on a scheme, then this not only does it have a Frobenius lift, the Adams operation, it actually has a delta structure. And the delta is the so-called lambda operation. If you know, so if you don't, this will be the last time I mention algebraic K-theory. And it's just a little side comment for those who know something about it. So delta is the lambda operation given by the symmetric function, which is x1 to the p plus x2 to the p. So you need a symmetric function in infinitely many variables. Which is this one. And it's not an accident that it's kind of very similar looking to that. Okay, so that's what a delta ring is and a p-derivation. You might, this is what I was alluding to before, you might complain that this is, we've used formula. So I'm going to show you that Witt vectors come naturally out of delta structures, out of p-derivations. You might complain that this definition is really based on formulas, but actually it's possible to eliminate the formulas from this. You can take the concept of a ring with Frobenius lift and then restrict to the p-torsion free case and then extend things to the general case in a kind of a universal category theoretic way that will somehow recover the definition of delta structure without ever having to write down any formulas. So for another just random side comment is you might ask, well, we've divided by p here. That's the well-known generator of the maximal ideal. It generates, but why didn't we take minus p? Well, you could have taken minus p, and you would have had a different, literally speaking, a different definition of a delta structure, a different definition of p-derivation, but there'd be a bijection between the two notions. So that shows already that this definition is actually not so sensitive to any kind of formulas you write down. But I think it's actually clearer to just write down the formulas. Okay, maybe a couple more, maybe a couple of exercises actually. So this is to show that that the assumption that R is p-torsion free here really is necessary. So it's an exercise, say R is an algebra over Fp, Fp being the integers modulo p, field with p elements, then so every Fp algebra has a Frobenius lift, namely Frobenius itself, but they don't all have p-derivations. And that's putting it mildly. So R admits a p-derivation. It's easy to say when this happens, and it happens if and only if R is the zero ring. So, okay, there's an exercise for you. So this, I guess the point is, this fails wildly. The bijectivity of this fails wildly the more p-torsion you have. And in fact, it's the same is true. All you actually need, you don't need that p is zero, you just need that it's nilpotent for any algebras over z mod p to the n. It's kind of the same proof. Okay. So that finishes the first part of this talk. The next part is on Witt vectors. I could pause to see. So, are there any questions or comments so far? Somehow, maybe I should say generalized lambda operations. So the usual exterior powers are given by the elementary symmetric functions. So lambda 1 is just by x1 plus x2 plus x3 plus lambda 2 is given by the second elementary symmetric function. This is a different symmetric function. It can be, by the theorem of symmetric functions, it can of course be expressed as a polynomial in the elementary ones. And this will be that same polynomial of the exterior powers. So in fact, let's see, we could do it quickly. What is, when p equals 2, you might even be able to do this in your head. Yeah, okay. I'm meaning you might be able to do it, not me. But you can, so you could write delta 2 is some polynomial in lambda 1, the usual, the first exterior power and the second exterior power, and even delta 3 you could probably work out. But when you get up to delta 5, it would be, you'd have to type it into a computer. Yeah. Any other questions? Okay, so now we're on to Witt vectors. So the goal, I'll just show you my cards already. So we have a category of delta rings. We have a forgetful functor to the category of all rings. Rings are always commutative, as I said. It turns out this functor has both a left and a right adjoint. I'll recall what those concepts mean. And the right adjoint is the Witt vector functor. So that's what I'm going to explain to you. So if you like, if you want a slogan, you could say the Witt vector ring of a ring A, W of A, is the, so this left adjoints are kind of free objects, right adjoints are kind of, you might call co-free objects. It's the co-free delta ring co-generated by A. There's a definition in one sentence. Okay, but that, I'll expand on that, and then, in fact, you don't even really need to know any category theory to understand things. So you might compare this with a few other situations. So instead of rings with a p derivation, we can look at rings with a usual derivation, an additive operator satisfying the usual Leibniz rule, and such that d of 1 is 0, just a usual derivation. So we can look at that category. Let me call them differential rings instead of delta rings. They're a little easier because the operator d, the derivation, is additive. But they're really not so different. And this will have also both a left and a right adjoint. And this one, which I'll tell you all about in a few minutes, let me call it the differential Witt vectors. It's sort of a stupid name because it's actually going to be something you've heard of already and are very familiar with. But you might compare this to, say, if C is an arbitrary ring, possibly even non-commutative. You have a forgetful functor from C modules to abelian groups. This has a left adjoint, which is tensoring with C, and a right adjoint, which is homing from C. And even another example, you might consider a situation with less structure, say sets. So you have category of set, say G is your favorite group, fix it. Forgetful functor, so you have a set with a G action. You form a category. The forgetful functor to sets has a left adjoint, which is just taking the free G set generated by your given set. That's just the product with G. Going the other direction is similar to this. You take a product of G copies of your set, and that has a G action, and that's the right adjoint. So what I claim, so soon you'll see what this one is. I'll just work that out, and you'll see. Then I'll show you what W is from this point of view, and you'll see it's kind of a perfect analog of all these things, and it's the most least surprising thing in the world. Okay, so now let's do So this one and this one are kind of already done. Now let's work out this, and then we'll proceed to this. So warm up differential rings. Okay, so I'll just tell you what this is in simpler terms. W diff of A is just the divided power series. So what do I mean by that? I mean the set of formal expressions sub a n t to the n on n factorial n at least 0, where the a n's are all elements of A. And I want to think of this fraction here as a formal placeholder. So this even works if you're not over an algebra over the rational numbers, so it's actually not literally a division, it's just a formal symbol. But we put it there so to remind us what the ring structure is, so it's the obvious ring structure. So let me just write it out. It's t to the m times m factorial times t to the n times n factorial is well, it's not t to the m plus 1 on m plus n on m plus n factorial, but it is a binomial coefficient. So that's m plus n binomial coefficient times that. So that's how the ring structure is defined. Then you extend linearly and I guess p-adically continuously. That determines a unique ring structure on this. The additive structure is, of course, component-wise. And it also has a derivation, which is just differentiate with respect to t. So d, so obvious differential ring structure, and the d is just d by dt. Okay, and now I claim that this is the right adjoint of the forgetful functor from differential rings to rings. So let me just write out what that means, unpack the concept of right adjoint, and then we'll just check that that's true. It'll be pretty obvious. So what is the right adjoint universal property? So if you don't know what a right adjoint is, I'm about to tell you. Suppose you have a differential ring R. So this means that there's a derivation going from R to R. A is just a ring, and we have a ring homomorphism G. So it just ignores the differential structure on R. The differential Witt vectors, they map down to A by just taking the constant coefficient, if you like, evaluating at t equals 0. Should I say that? Sum a n t to the n on n factorial is sent to A0. And what we have to show is that there exists a unique lift, which we'll call G tilde, from R to W diff of A, which is now a homomorphism of differential rings. So this also has a differential d by dt. So this vanilla ring map lifts to a unique differential ring map. So that's what the definition of right adjoint is. And in fact, it's easy to just say what it is. So G tilde of an element R, you just take the Taylor series of R in a formal sense and then apply G to every coefficient. So I'll say, in quotation marks, G of the Taylor series of R. But what does that formally mean? It means the sum of it's just this. So you take all the derivatives of R, of your given element R, they're different elements in this ring big R. You apply G to them all. You get an infinite sequence of elements of A, and you form the Taylor series out of that. Okay, so one needs to check that G tilde is a differential ring map. I claim that this is obvious. Basically, it boils down to the fact that the Taylor series of a product of functions is the product of their Taylor series. The Taylor series of a sum of two functions is the sum of their Taylor series. Taylor series of a derivative of a function is the derivative of the Taylor series of the original function. So, of course, you know all that well from analysis, but it's sort of even true formally. So I'll let you check that yourself. Okay, so that's what it is. Those are the differential Witt vectors. And so I'm about to tell you that W is basically the same thing as these. Before I do, let me say a few words about an alternative point of view. The problem is that we had, in this case, we could kind of give a nice definition because we had heard of power series before. But the actual Witt vectors, there's no simple construction that we've heard of before in some undergraduate class that we can build off of, so we kind of have to build it up from scratch. So rather than thinking of a power series as a series, I'll just think of it as a vector of coefficients. So this is, if you like, a vectorial point of view. So we can think of W diff of A as an infinite product of copies of A, where we just encoding the coefficients. So the series some an on n factorial is identified, I'll write equals, with the vector of its coefficients. Okay, and then, so we can just think about these ring operations as operations on this infinite product. And let me say, so we'll write that down in a second, but from that point of view, differentiation is just shift to the left. Right? Just if we apply to this, you get A1, comma A2, comma A3, and so on. Okay, so, and then from this point of view, our G tilde will take an element little r to the vector of G applied to all of its derivatives. Okay, but now you'll see, let me kind of turn things on their head. You'll see that somehow, like, of course, this is what it has to be, because, right, you can see from this point of view that G tilde is, in fact, the unique set map, the unique d-equivariant set map lifting G. Ignoring the ring structure, it's just the unique map which lifts G, which is compatible with the two differentiation operators, simply because if you differentiate this vector, that means you shift it down once, and then if you project it, you have to get, the thing you get is this, which has to be exactly the G of what you get when you first apply differentiation, and then you go through here, and then you project onto the zeroth component. So really, this is the only possibility, even at the level of sets, completely ignoring the ring structure. So keeping that in mind, we can try to, well, we can try to apply that to the actual Witt vectors. So how are we going to do that? So maybe I didn't quite say this, that another way of saying it is that the ring structure on this infinite product, so this is the unique set map which is compatible with D lifting G. The ring structure on this is then forced to make this actually a ring homomorphism. So, right, so the point is that the ring structure on the infinite product is then forced on us. So, and it's even forced in a very explicit way. So it is what I'll call a purely syntactic re-expression of the Leibniz rules. But for the higher order derivatives as well. For the nth derivative operators. So what do I mean? Well, let me just write out the ring structure. Okay, so beg your indulgence while I write this down. So if you multiply two power series, right, you get, and then we have our binomial coefficient. And then okay, so the I plus jth coefficient of the new power series is this polynomial expression in the coefficients of the original power series. So we can write, so which letter do I want to use? K. So it's given like this, where this is the nth entry. But then what is the Leibniz rule, the product rule for the nth derivative operator? It's exactly that. So we'll compare that to the nth derivative of a product is the sum over I plus j equals n, or binomial coefficient times the ith derivative of the first factor and the jth derivative of the second factor. And that, this right here, is the same. Well, not literally the same, but if you write down this polynomial, you can just tell your computer how to output that polynomial. And in fact, that's the only, it has to be that way because if you want to make this map G tilde multiplicative, then the law at the nth, I mean, if you just somehow sit down and ponder it a second, you'll see that that's the only option. Okay, so now we're in a perfect position to go back to the usual Witt vectors, because the point is that these Leibniz rules determine everything. We can just, the differential Witt vector functor here can be defined as an infinite product. The derivative is the shift operator, and the ring laws for at the nth component are precisely encoded by the Leibniz rule for the nth derivative. So now we just do that for the usual Witt vectors. So back to W and delta rings. So we do the same thing. W of A is an infinite product. With the ring structure at the nth component given by the Leibniz rules for the nth iterate of delta now, there's no derivation anywhere in sight, so it's now delta, with respect to addition and multiplication. So before, we didn't need to talk about the Leibniz rule with respect to addition, or rather, I mean, the fact that the Leibniz rule for the derivative of a function is trivial, the nth derivative of a sum is the sum of the nth derivatives, is exactly the statement that the additive structure on these vectors is component-wise. You don't, the polynomial, you don't need a more sophisticated polynomial that mixes up lots of the entries. That will not be true any longer in this context. And And that's the reason for kind of the somehow expository complexity of the Witt vectors, but that's really the only reason. Everything else works just exactly the same. So maybe I should have said, I didn't, so if, I didn't talk about, okay, right, so say the second derivative, second arithmetic derivative of x times y, how do you expand this? Well, you just expand, do it once, so this is x to the p times delta of y plus delta of x times y to the p plus p delta of x times delta of y. And then you have to expand this thing using first, well now it's, you would never want to write this down because now you have a sum of three things. So you have to write down the law for delta of summing three things up, which you get by applying the law for delta of a sum of two things twice. And then on each of those you expand it out using multiplication. But eventually you will get to some polynomial in x, y, delta of x, delta of y, second derivative of x, second derivative of y. In fact, it's a unique polynomial, which maybe I'll leave as an exercise. What exercise am I up to? Can't remember. 3. These Leibniz rule polynomials are in fact unique. So somebody else might choose to break this down in a different way, in a different tree, but in the end, at the end of the day, you'll get the same polynomial in these 6 indeterminates. I think that's actually not technically, it's not at all hard to show, but I think it's actually not technically necessary for what, even though somehow it looks like it's necessary, I think you could just choose whichever one you want, and then this construction will be the right adjoint with respect, and therefore the right adjoint is unique. So I think I think in fact, verifying this is not technically necessary, but it's certainly very easy to do. Okay, so let me just write out what it is. The first. Maybe I should have done this 5 minutes ago. So the Leibniz rule, so the first component is the 0th iterate of delta, and that's the identity operator. So in fact, it's so easy. I'll just, it's just this. Let me write down the next component, and then if it's not clear what's happening here, then the 0th component will be easier. So the derivative of a product, the derivative of a sum, the delta of a sum, which I erased, is this polynomial, and what is it? It's a1 plus b1 minus the sum 1 on p choose I, a0 to the I, b0 to the p minus I equals 1 to p minus 1. So this, if you'll remember, unfortunately I rubbed it out, is exactly the polynomial for delta of x plus y, but instead of things like a sub 1, I mean now a sub 1 is written where, well, okay, what was it before? It's delta of x plus delta of y minus the sum 1 on p choose I, x to the I, y to the p minus I. Of course, x is the 0th iterate of delta applied to x, and y is the 0th iterate of delta applied to y. So x corresponds to a0, y corresponds to b0, a1 corresponds to the first iterate of delta applied to x, and b1 corresponds to the first iterate of delta applied to y. And similarly for multiplication, a0, a1 times b0, b1 is a0, b0. Again, the Leibniz rule for the 0th derivative of a product is just the product itself. And then at the next component, we do the one that we discovered before. So a0 to the power p times b1 plus a1 times b0 to the power p plus p a1 b1. And then they keep going. And just to be complete, the additive and multiplicative identities. So the zeroth derivative of 0 is 0. The first derivative, delta of 0, is also 0. So all higher ones are 0. 1, the zeroth derivative of 1 is 1, right? The first derivative of 1 is 0. I'm talking about the delta derivative now, of course. And then all higher ones are 0. Okay, and then the adjunction property is, well, I won't erase that because it's exactly the same. One thing I should also tell you is that delta, I'll put it here, delta is again just a shift operator. So delta takes a vector a0, a1, and so on, and shifts it to the left just like it did with differentiating power series. And then our G, well, we have R, we have a delta ring structure on R, A, we have a ring homomorphism G, we have now the ring of actual Witt vectors. This is, again, just projection onto the initial component. Should I write that down? Just as it was there. And then the unique lift, well, just as a set map, it has, we know there's a unique set map, which is, there's a delta here, which is our shift. There's a unique set map, which is equivariant with respect to delta lifting it, and it takes R exactly to G of R, G of delta of R, G of delta squared of R, and so on. And we know this is a ring map by construction. So it's the unique set map, equivariant with respect to delta. I won't write it. And it's a ring map by construction. So, in fact, G tilde is the unique ring map lifting G. Therefore, W is obviously functorial in A, so therefore W is the right adjoint. Okay, so that's what the ring of, or maybe I should say the delta ring of Witt vectors is. What time did I start? 2 more minutes. Okay, good. Okay. You might ask how this compares to the usual definition of Witt vectors. In fact, there's a canonical isomorphism between our construction and the usual construction that Witt wrote down very clearly in the 1930s. It's also written down in everywhere, in Serre's book, Local Fields, in Bourbaki, many places. And their construction is also gives kind of an exotic arithmetic ring structure on this infinite product. But it's a different one. The first 2 components are the same, but they differ after that. So there's a canonical map between our W of A, canonical isomorphism, between our W of A and the traditional W of A, but it's not the identity. So what I'd like to do, then the main goal of the next 2 lectures is to explain that and explain some other things kind of in this surrounding area of exposition. Okay, thanks. Yeah, it is. I mean, for instance, this, the integrality, I didn't emphasize that. These coefficients are all integers. That's kind of the point.
Okay, if you restrict these value of rings where a 6 is vertical.
Oh, but then if you're, well, you also need a Frobenius map modulo 6.
Just
I somehow don't think, I think it probably can't possibly work, but I can't give you a good reason why. But I'd be happy to discuss it more if you give me a chance to think about it. Yeah. 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 Okay, so here it is. There exists a unique. I'll do this. I'll call it, say, p plus n. This is going to be the polynomial for the Leibniz rule for the nth iterate of delta with respect to addition. So there's a unique polynomial with integer coefficients in these indeterminates such that delta of x plus y is equal to p n plus of the ith iterate of x, comma, the ith iterate of y. And similarly for multiplication. Yeah. Yeah, so maybe I should say this. I said it before, but in my mind, this is more like a point of view on the Witt vectors rather than theorems. But anyway, the realization that this could give a complete account of the theory of Witt vectors is due to Joyal. And also, it's important to mention Bouillon, who was never so concerned with the Witt vectors, but was very concerned with delta rings. So he kind of, anyway, he didn't write things about Witt vectors, but he wrote kind of everything else he wrote papers about. Yeah, so you can do the multiple, and Joyal also did discuss the multiple prime Witt vectors. So what you need to do, if you insist on doing it from this point of view, you want the Frobenius lifts to commute. So you want, now let me say, I'll write phi sub p for the Frobenius at p. So you want phi sub p composed with phi sub q to be phi sub q composed with phi sub p. And, but now you want to express that in terms of the deltas. Because we want, so we have a bunch of deltas. We have, well, say we just do 2 primes. You could take any set of primes you like. So we have 2 delta operators, but we want their corresponding Frobeniuses to commute. If you write out that law in terms of the deltas, you'll have some coefficients, some p's and q's in the coefficients. And once again, you can actually divide by them and get polynomials with integer coefficients. So you get that delta p composed with delta q minus delta q composed with delta p is some explicit polynomial in, let me put in an x. Let's see, what is it in? I guess it's in x, delta p of x, delta q of x, and I think nothing else. So is that right, Arnab? Do you remember? Anyway, some explicit, it kind of has to be this. So this will be some specific thing you can write down, depends on p and q, but nothing else. And it's equivalent to this statement in the torsion-free context. You need p torsion-free and q torsion-free, but is a stronger axiom in general, and that's the one you want to choose. And then if you do that with respect to all primes, then you get a lambda ring. Instead of a delta ring, you get a lambda ring, as people in K-theory talk about, and the corresponding notion of Witt vectors is the big Witt vector functor. Yeah, that's right. Yeah, so yeah, I'm really glad you mentioned that. So usually Witt vectors are thought of as a machine for lifting things from characteristic p to characteristic 0. And I think that's an important aspect of them, but I think it's not the most important. The most important one is giving rings a Frobenius lift where we interpret Frobenius lift to mean Frobenius lift in an intelligent sense, which means a delta structure. And it just so happens that, well, okay, anyway, let me be bold. It just so happens that that device has the effect of lifting things from characteristic P to characteristic 0. But, well, anyway, I think this is a very natural development. There's nothing, there's somehow, you can give, and I've written in kind of section 1s of a couple of papers I've written, there's sort of a version of this exposition with no formulas. It's just all category theory. So it starts with the concept of Frobenius lift, then does a bunch of category theory, and ends up with the Witt vector construction. So it's somehow a purely effortless thing, or rather, it follows from just general nonsense once you input the concept of Frobenius lift. So that's why I think this point of view is better than the traditional point of view. Yeah, I don't, it's kind of a bold statement, but I don't know if you insist on coming up with a machine for lifting rings from characteristic P to characteristic 0, I don't think it's clear why the original Witt vector construction is an inevitable thing. I guess that's, for me, it's my kind of primary concern in mathematics. I kind of want everything to seem inevitable. And if somebody just randomly, some genius in 1936, thought of some crazy construction, and then we kind of all use it because he's so smart and it's been so useful, okay, that's good, but I sort of, maybe there's a better version of it or something.